Validation is a cornerstone of robust time series analysis. It ensures that any model we develop is not merely fitting historical noise but genuinely capturing underlying patterns. This step is crucial for building trust in our predictive capabilities. The primary goal of validation is twofold: to confirm the model's accuracy on known data and, more importantly, to ascertain its ability to generalize effectively to future, unseen observations. A model that performs well only on its training data is of limited practical use. Time series validation fundamentally differs from traditional cross-validation techniques applied to independent and identically distributed, or IID, data. The unique structure of time series data demands a distinct approach. The defining characteristic of time series is its inherent temporal dependency. Observations are not random samples, they are ordered sequentially and often exhibit significant correlation over time. This temporal structure cannot be ignored. This inherent autocorrelation means that future values are often influenced by past values. Consequently, specialized validation techniques are absolutely necessary to properly assess model performance. These specialized methods serve a critical purpose: to prevent data leakage, where information from the future inadvertently influences the training process. They ensure that our performance estimates are reliable and truly indicative of future forecasting ability. The holdout method is the most fundamental approach to time series validation. It is also widely known as the fixed origin method or simply a train test split. This technique provides a straightforward way to evaluate a model. The process involves dividing the entire time series into two distinct segments. The earlier observations constitute the training set, which is used to fit the model. The later observations form the validation or test set. This segment is reserved exclusively for evaluating the model's performance after it has been trained. Model training is conducted exclusively on the training data. The model learns patterns and relationships solely from this historical information, without any exposure to the future data. Model evaluation then occurs on the subsequent validation set. This step assesses how well the trained model predicts outcomes for data it has never encountered during its learning phase. This approach effectively mimics real-world forecasting scenarios. In practice, future data is always unknown, and models must predict based only on past information. Its primary advantage lies in its simplicity and ease of implementation. It provides a quick and intuitive way to get an initial estimate of model performance. However, a significant drawback is that the performance estimate can be highly sensitive to the chosen split point. A different split might yield a substantially different performance metric. Furthermore, this method doesn't fully utilize all available data for validation. A large portion of the data is used for training, leaving a single, often smaller, segment for testing. To address the limitations of a single split, rolling origin cross-validation is widely employed. This advanced technique offers a more robust and comprehensive evaluation. It is also known by several other names, including walk-forward validation or time series cross-validation. These terms highlight its dynamic nature in evaluating models. The primary purpose of this method is to overcome the drawbacks associated with a static, single train test split. It provides a more stable and reliable performance assessment. The process involves executing multiple train test splits across the time series. Each split represents a different point in time, allowing for varied evaluation contexts. In each iteration, the training window progressively expands or slides forward in time. This means the model is trained on an increasing amount of historical data or a moving window of data. Evaluation is then performed on a fixed-size forecast horizon immediately following the training data in each iteration. This ensures that the model is always predicting into a future period. The performance metrics obtained from each iteration are then averaged. This aggregation provides a more robust and less volatile estimate of the model's true predictive capability. One key utility of rolling origin cross-validation is its ability to evaluate model stability. It shows how consistently the model performs across different time periods and data distributions. It is also highly useful for evaluating performance over different periods. This helps identify if a model's accuracy degrades or improves during specific historical phases. This method is particularly crucial for models that adapt over time. It allows for the simulation of continuous retraining and reevaluation, mirroring real-world deployment of adaptive forecasting systems. Beyond the fundamental and rolling origin approaches, other specialized validation methods exist for specific scenarios. These techniques address unique challenges in time series data. Blocked cross-validation is one such method, designed to mitigate the impact of autocorrelation. It achieves this by using consecutive blocks of data for training and testing, rather than random or purely sequential splits. This ensures temporal order within blocks is maintained. For models that are computationally expensive or when data is scarce, particularly in financial time series, purged and embargoed cross-validation can be considered. This method is designed to prevent subtle forms of data leakage. A purge period is introduced between the training and testing sets. This gap prevents information leakage that might occur due to overlapping features or labels, especially when observations are highly correlated. An embargo period is also implemented. This prevents look-ahead bias, ensuring that no information from the test set, even indirectly, influences the training process. The choice of performance metrics for time series validation is critical and differs from those used in classification or standard regression. These metrics must accurately reflect forecasting objectives. Common metrics include mean absolute error, or MAE, root mean squared error, or RMSE, mean absolute percentage error, or MAE, and symmetric mean absolute percentage error, or SMAE. Each offers a different perspective on forecast accuracy. The selection of the appropriate metric depends heavily on the specific forecasting objective and the characteristics of the data. For instance, MAE is useful for understanding error relative to the actual value, while RMSE penalizes larger errors more heavily.